Hello, my name is Nathan Drenkow, and I'd like to present our work on attack-agnostic detection of adversarial examples. We're all well aware that adversarial attacks pose a threat to safety-critical systems. Methods for explicitly detecting adversarial examples provide a strong line of defense against these attacks. While significant work has been done in this area, current approaches often train detectors in a way that requires both clean and adversarial examples. These examples necessarily force explicit assumptions about the attacker's strategy and goals. Furthermore, the sizes of these data sets are often large, which may be impractical in certain scenarios. Our method based on random subspace analysis aims to directly address these limitations. Consider a deep neural network which receives input X and predicts output Y hat via a series of computational layers, which produce intermediate feature space representation Z. We can compute these representations for our test point, as well as for calibration data where the class labels are known. Class prototypes can be computed by averaging representations conditioned on their label. And then in this feature space, the distance from a test point to the closest to the class prototypes provides a proxy for classification, where the predicted label is that of the closest prototype. When an example is adversarially and successfully perturbed, its closest prototype shifts. To perform detection, we ask, can we probe these representations in such a way where the resulting behavior is predictive of an adversarial example? To do this, we use multiple random projections to measure to the consistency of the preferred class label across these random subspaces. Each projection is computed by sampling a random matrix R, which is used to project the representation Z to its lower dimensional random subspace Z prime. Then we can measure the self-consistency by determining whether the test point's preferred label is consistent across subspaces or inconsistent. By repeatedly computing these projections, we predict that adversarial examples will exhibit greater inconsistency relative to clean examples. So why should this work? The Johnson-Lindenstrauss lemma, a classical result, provides a guarantee that pairwise distances are preserved under random projection, such as those between the test point and class prototypes. The result is a worst case bound, but actually empirical results suggest that it may be even better in practice. Furthermore, Ilias et al. Demonstrated the existence of robust and non-robust features learned by deep neural networks, where the non-robust features are those that are most likely to be manipulated under attack. We hypothesize that different random projections are likely to amplify the effects of these manipulated features for adversarially attacked images, thereby causing greater inconsistency across random subspaces. To perform detection, we first compute the class prototypes using a small calibration data set composed of clean-only examples, which makes our approach attack agnostic. Then at test time, we compute the layer-wise activations for our test examples. And then for each example, we project the activations into a set of random subspaces where we determine the closest class prototype in each subspace. Then our decision rule simply determines the fraction of class consistency across those subspaces and rules the examples adversarial if the consistency is not sufficiently high. Our results indicate that our method reliably detects adversarial examples across a variety of data sets, model architectures, and attack strategies for both untargeted and targeted attacks. Our sensitivity analyses further indicate that our detection method is not overly sensitive to the number of random subspaces or their associated dimension. Of course, future work could improve these results by examining more sophisticated detection rules. In summary, we've proposed a novel adversarial example detection strategy, which is agnostic to the attacker strategy and goals, and which requires only a small amount of clean calibration data. Our results indicate strong detection success across a variety of scenarios. And so if you'd like more details, please check out our paper or come talk to us at our poster. Thank you.